Welcome back, everyone. So today we're going to look here at working quantitatively with gravitational fields. Here's our key knowledge focus for today. So we're going to analyze the use of gravitational fields to accelerate mass, including gravitational field and gravitational force concepts, but today we're only focusing on the field. So we're going to look at how we can calculate the field strength around an object. So, as this highlighted in Quail Equation implies, that's what we're going to be working with. So we say little g is the gravitational field strength, and we measure gravitational field strength in units of newtons per kilogram. That's a really interesting quantity, really interesting unit. We'll look at that in just a second. What's on the other side? So we've got big G, called the gravitational constant. This has a value of 6.67 times 10 to the negative 11. Don't worry too much about the units. The units are the units to make the equation work out. But just notice it's a very, very small number. Okay, and this is a experimentally found value. Okay, it's something that we've tested over a lot of experiments, over a lot of years, and it's a value that we've come up with to make this equation work out. M is the mass of the object that's exerting the field. We use kilograms. And R is the distance from the center of mass of the object exerting the field. And we use meters. Okay, always kilogram, meters, and seconds unless otherwise specified. So center of mass, that's a really important thing to understand. So we've got basically these objects exerting gravitational fields, such as the Earth or the Moon or the Sun or whatever. And we typically think of them as spherical, but we also need to think of them as having uniform density. So they're made of one material and one material only, and there's no material bunched up on one side and spread out over another side. It's all sort of uniform. Okay, it's all the same everywhere. Now in this idealized physics world, the center of mass would be the geometric center of the object. Okay, if you can consider it a sphere, it's just the center of the sphere. Okay, so if I'm talking about finding the gravitational field at a point up here somewhere, then I need to find the distance between that point and the center of mass of the object. This value here is the R that we're putting in the equation. Okay? So this is how we can quantitatively work out a value for the field strength. Okay? Now let's just quickly talk about what this means here. Newtons per kilogram. Okay? So one way to think about the gravitational field or the gravitational field strength is to think about what it does to something. Okay? What does the gravitational field do to an object? Well, in the last video we talked about how the gravitational field can be considered this warping of space. And if you were to put an object in the field, then the object would experience a force. Okay? Now, is the force equal for any object that we put in the field? Like if I put a 5 kilogram object in this field, will it experience the same force as a 10 kilogram object? Well, it turns out no, and we can do measurements to test this. But the field value itself tells us how much force an object would experience per kilogram it contains within its mass. Okay, so the field is a force per unit mass. Okay, and what that means is if I go to some point out into space and the field strength happens to be 9.8 newtons per kilogram, what that tells me is that if I put a mass at that spot and the mass has 1 kilogram, then this mass will experience 9.8 newtons of force. If I place a 2 kilogram object at that spot instead, it will experience 2 times 9.8 or 19.6 newtons of force, and etc. and etc. Okay? So the field strength, this number here tells you that for every kilogram the object in the field contains, it will experience that value of force. Okay? Now, if we can sort of write that as an equation, we'd write it something like this, that the field is equal to the force per mass, or force per unit mass. If you rearrange this, you end up getting F equals mg. Now, you've used F equals mg before. Okay, in area of study 3, you calculate the gravitational force on an object. It's F equals mg. So what does g remind you of? Okay, think about it. If you haven't already read the last line in big bold red letters, it's acceleration due to gravity. Okay, that little g here, the same little g that we're talking about when we calculate field strength, those are the same thing. Okay, or you can consider them to be equivalent values. All right, one is just when we're talking about a force. One is when we're talking about the strength of a field that's exerted by a mass. All right, but the two things are equivalent, and you can interchange them in calculations so long as you know what you're doing. So keep that in mind. We'll talk about that later on when we talk about gravitational orbits and things like that. Okay, but that's just a way that we can consider what a field strength represents. Okay, it's the amount of force per kilogram that an object would experience if it was placed at that point in the field. Okay, now just before we can start doing a few questions, the altitude is a way that some examiners can throw you off and trick you and make sure that you're trying to pay attention. So I've got to look at what that means. The altitude is the height above the surface of a body. Okay, so it's the height above a planet or the height above a moon. It's not the distance from the center. Okay, the altitude is from the surface to a point somewhere above the surface. So when we are calculating the gravitational field strength, okay, let's go back to this picture here for a second. The altitude of this point above the surface of this planet would be this distance here. Okay, I'll call that big A for altitude. All right, now I can't put that value into my equation because it's not the right distance. Okay, I have to add this little bit here, which would just be the radius of the planet, the radius of the body in question. All right, so that's what we need to consider when we've been given the altitude in a question. Okay, we're probably going to have to add the altitude to the radius of the object, or if we're doing things another way, we might have to take it away or do something with the radius of the object itself. Now, consider this. Okay, look at the last dot point. The altitude only plays a great role when it's of comparable size to the radius of the body. So let's say I've got a planet and I zoom out. Okay, so that's the Earth, but I've just zoomed out a lot. Now let's talk about a point in space all the way up here. Okay, what you should notice is that the difference between r, little r, which is the distance from that point to the center of mass of this object, that is pretty much equal to the altitude of that object, okay? Because the only difference is this little bit here, the radius of the mass. So when your point in space is really, really far away from the object, you can ignore altitude. You can just treat altitude as the actual distance between the center of mass, okay? If you're just doing a sort of back of the envelope calculation and you don't have to be very, very precise, then you can just make that assumption. All right, and if you keep zooming out, then they become basically equal. So let's see how we can use altitude in a question. So here's a question. Compare the gravitational field strengths of the following altitudes with that at the surface of the Earth, which we're taking to be 9.8, and there is some data there about the Earth. So, okay, so it's asking us to work out the gravitational field strength at an altitude of, first, 0.1 Earth radii. What does that look like? Okay, so here I'm going to draw a picture of the Earth, or a part of it. That right there is the radius of the Earth. And we're at an altitude of 0.1 times that distance, which might be something like that. Okay, that's probably a bit too high, but you get the idea. That distance there, 0.1 times the Earth's radius. Okay, that's our altitude. Now our job is to work out G at that point. So what value of r, little r, are we going to be putting in our equation for field strength? Well, r is the distance from that point to the center of mass, so we've got to do that whole distance there. All right, what's that distance? Well, I've got 1 Earth radius plus 0.1 Earth radius. So I've got 1.1 Earth radius. There you go. That value there is equal to the little r that we put in our equation. Okay, and you can do the same thing for all of these other altitudes. Okay, I'm not going to waste time working them all out. You can do that yourself. Let's just work out the first one though. So g at that point there, if I put in all my data, okay, 5.97 times 10 to the 24 kilos for Earth's mass over this value of r here, this little r, which is 1.1 times the Earth's radius. What's the Earth's radius? 6.4 times 10 to the 6 meters. And we have to square that. That's really important. That's where people stuff up the most. They forget to square the radius underneath this fraction. Okay, so make sure you square it. Just pay attention to what you're doing. That's where you're going to lose silly mistakes. Anyway, that turns out to be something like 8.03 newtons per kilogram. Okay, that made sense. You're moving further away from an object. The field strength is getting weaker and weaker. So there you go. Okay, and all you've got to do really is replace this number here with the number you work out based on the altitude you've been given. Okay, nothing too crazy. Seems pretty easy so far. You just got this nice little equation. Not much can really be asked of you. You know, what is the field strength at this distance from the center of mass of this object? Okay. Let's do one more, see if we can use the equation again. So what do we got? Calculate the gravitational field strength at the surface of the sun, which has a mass of 2 times 10 to the 30 kilograms and a mean radius of 7 times 10 to the 8 meters. So here's the sun. If it's a sphere, the distance from the center to the outside is this, 7.0 times 10 to the 8 meters. Cool, and it's asking us what is the field strength at the surface. So what is the field strength at 7 times 10 to the 8 meters from the center of mass of the sun? Cool, so now let's just plug in the equation and work it out. And you get around 272 newtons per kilogram. Okay, quite a lot larger than what is experienced on Earth. Okay, but again, it's just a plug in and solve question. Nothing fancy going on here. You've got an equation for field strength, put numbers into it, work it out. All right. Another variation on a theme. So find the altitude at which the gravitational field strength of the Earth is half of that at the surface, or half of 9.8. Again, you've got the data of the Earth there. So what it's asking us to find is some point up here where the field strength is half of 9.8 or 4.9. And it's asking to find the altitude. So it wants us to write this distance here as our final answer. Okay. Now what we should be able to do, because I've got the radius of the Earth, is I can work out, if that's the center of the Earth there, that's the radius of the Earth. Using the formula G equals big G times m on r squared, I should be able to work out r, that distance there. And because I know the radius of the Earth, I can just subtract that from r to get a. All right, so that's our goal for this question. So work out a value for little r, use that value with the radius of the Earth to work out a. Let's do that. So rearranging this equation here to get little r, I get square root of big G times m over little g. So r is going to be equal to 6.67 times 10 to the negative 11 times 5.97 times 10 to the 24 over little g 4.9 at that point up here. Okay, and what I end up getting is something around 9.1 times 10 to the 6 meters. So that's r, little r. Okay, we need A. So I'm going to subtract the radius of the Earth from this. So that's little r that I'm writing now, minus the radius of the Earth. And I end up getting something around 2.61 times 10 to the 6 meters. Okay, so that's the altitude above the surface that we're talking about. Right, whereas this number here is the distance from the center of mass. Cool. All right, so that's pretty much everything that you can do with altitude. Not too crazy there. All right, let's look at one more. This is from 2018 VCAA exam. And again, they're just trying to trick you. Okay, so you really got to read the question. Make sure that you know whether it's talking about altitude or center of mass or what. So it says at one point on Earth's surface at a distance r from the center of the Earth. So let's draw a picture. It's r. The gravitational field strength is measured as 9.76. So that point there on the surface, 9.76. Which of the following is closest to Earth's gravitational field strength at a distance of 2r above, in bold, very important, above the surface of the Earth at that point? So we have to now go from this point on the surface to an altitude of 2r. So that's 1r. There's 2r. That total distance is 2r. So what is the distance from the center of the Earth in terms of r? Well, we've basically tripled our distance. So the total distance from the center of the Earth is r plus another 2r is 3r. All right. Now we're going to have to use something we haven't really talked about yet, and this is the inverse square proportionality of the gravitational field strength. Okay, look at this equation. We're going back a few slides. What this equation is telling us is that the gravitational field strength is inversely proportional to 1 on r squared. What the hell does that mean? Okay, well, basically, in simple terms, if I double my distance, okay, what I'm going to do is I'm going to replace r with 2r. If I replace r with 2r, I get 1 over 2r squared, like that. If I expand that out, I end up getting 1 over 4r squared. I can separate this fraction as 1 over 4 times 1 over r squared. This is the original field strength, but we've made it a quarter of what the original one was at this new location of 2r. Okay, so if you play around with that number, you'll see that if I triple my distance, I'll end up getting 1/9 of my original field strength. If you quadruple your distance, you end up getting 1/16. If you multiply your distance by 5, you get 1/25 of your original field strength. Okay, that's how an inverse square law works. Okay, you have to square your new distance in order to find how weak your field strength is going to become. Okay, and this also works in reverse. Okay, if I half my distance, that means I'm replacing the r in my equation with half r, or r on 2. So what I'll get is something along the lines of this, which expanding out becomes 1 over a quarter r squared. 1 divided by a quarter is 4. Okay, so by halving your distance, you end up multiplying the field strength by 4. If you divide your distance by 3, you're going to multiply your field strength by 9. Okay, and that's how the inverse square law works. And we'll see a graph of what it looks like in a second. Okay, let's go back to the question. All right. Okay, so back to the question. We've tripled our original distance. Okay, originally we were just at r. Now we've gone to 3r. What's the field strength? Well, we just saw that if you triple your distance, your field strength decreases to 1/9 of what it originally was. If our original field strength is 9.76, 9.76 divided by 9 is around 1.08 newtons per kilogram. So we have option A. Okay, it's based on how this inverse square proportionality works. Make sure you understand it. Okay, so this is what I was talking about the graph of field strength versus distance. Okay, now for those of you who do methods, you might recognize the graph of 1 on r squared looks something like that. Okay, so the further away that you go, the weaker your field strength gets, and it gets weaker by 1 on r squared, or 1 on distance squared. And that's what this portion of the graph is saying here. All right. But you've also got this other straight line portion. Let's just read the question and see what's going on. Assume that a journey from approximately 2 Earth radii, or 2 RE, down to the center of Earth is possible. The radius of Earth, RE, is 6.37 times 10 to the 6 meters. Assume that the Earth is a sphere of constant density. A graph of gravitational field strength versus distance from the center of Earth is shown in figure 4. Part A. What is the numerical value of y? So at this point here, what is that value? Okay, think about where you are. Okay, try and picture yourself in this situation. If you are at a distance from the center of the Earth of 1 Earth radii, where are you? Think. That's right. You're at the surface of the Earth because you are at 1 Earth radii. Okay, that's all it is. So you think, okay, what is the gravitational field strength at the surface of the Earth? 9.8. Okay, that's all it is. No calculation required. 1 mark. That's it. Part B. Now, this question lots of people got wrong. I think something like 80% of people managed to get 0 marks for this part B. You can go and read the examiner's report and see why. But it says, explain why the gravitational field strength is 0 newtons at the center of the Earth. So that's this point right here. Now, what you've got to think about the Earth as being made of is a whole bunch of tiny little spheres. Okay, which it kind of is. I mean, it's made out of atoms and molecules and things like that. Okay, so if I draw a picture of the Earth, I'm making it very simplified. Okay, that's the Earth. A bunch of spheres stuck together. Tiny little spheres. And you're talking about the point right in the middle. Think about what's going to happen to the field at that point based on the field exerted by all of these little spheres. Okay, this sphere here will exert a field that way. But you can pick the opposite sphere on the other side, which will exert a field in the same magnitude, just in the opposite direction. Okay, it's a bit hard to see. Actually, it's a really crap drawing. Let's make it slightly bigger. Okay, so this one here will pull that mass that way. But this sphere on the other side of the Earth will pull the mass down that way, in effect cancelling it out. And you can always pick any point to match any other point on the Earth, which will always cancel out the gravitational field from one another. Okay? And that's how you explain part B. Okay? And it's all based on the fact that we're assuming the Earth is a sphere of constant density. So there's nowhere on Earth that's got more density than others. That means you can always pick a point such that its gravitational field will cancel out with another one somewhere else in the opposite location. All right, and how you want to articulate that is up to you. Again, go and look at the examiner's report. They give a sample response there. All right, and read where people went wrong. I'm not going to go through that here. All right, that's it. Sorry for the long video, but that's really all you're doing when you're calculating field strength. Okay, there's not anything else that we're talking about here. That's it. Okay, field strength is calculated using this formula. It has units of newtons per kilogram, which means it is a force per unit mass. Okay, so the field strength tells you how much force an object experiences for every kilogram that it contains. The gravitational field relies on an inverse square rule. Okay, so you double your distance, the field strength reduces to 1/4. You triple your distance, the field strength reduces to 1/9. You multiply your distance by 4, your field strength reduces to 1/16. It also works in reverse. If you halve your distance, field strength multiplies by 4. If you reduce distance to 1/3, field strength multiplies by 9, and so on and so on. You've got to remember altitude is the height above a surface, and you need to factor that in when you are calculating field strengths relatively close to the surface of a planet or a mass. You have to usually add the radius of the planet to the altitude to find the value of little r that you're putting in your equation, and that's sort of stated in the last dot point there. Okay, so we'll leave it there. Here's some summary questions to think about. We just talked about that, so you should have no problem answering that. All right, we'll stop there, and I will see you next time.